we are. Anybody have any questions just for before we get started? Okay, it's 12:35, so I'll begin. So I want to speak today about the carbons that are in so-called region 3 of the diagram that we've been speaking about. And this is an example of a carbon prepared from sugar, pyrolyzed at 1050 degrees C. It has this very long reversible capacity plateau and a sloping region, giving you overall about 550 milliamp hours per gram of reversible capacity. So pretty interesting. So like I said before, Ed Buell, one of our students from about 1996 to 1999, did a lot of this work. And what's happening here is take a sample of sugar and you heat it in argon at different temperatures and then measure the performance of the material. And there's a few things that you can notice happening to the voltage curve. The first is this region showing hysteresis gets smaller and smaller, and then eventually by 1200 degrees C, it looks like, you know, pretty reversible without a gap between charge and discharge, or not without a large gap between charge and discharge. And this corresponds to the elimination of the hydrogen from the material, because this 1 volt plateau during charge is thought to be from the hydrogen. And again, these curves are shifted up for clarity by 3 volts. They're not really like this. And then the second thing that happens is the irreversible capacity becomes shorter and shorter and shorter. This is also thought to be associated with the reduction of the hydrogen content. And then the final thing you'll notice is that the length of the low voltage plateau gets shorter and shorter, and by 1400 it's almost gone. Okay, so we wanted to understand, first of all, where does the low voltage plateau come from, and why do things change the way they do with heating temperature? So here's X-ray diffraction patterns for the sugar sample heated at 900 degrees and 1400 degrees. And you would say, based on these patterns, there's not very much difference between them. And it's not expected because it's a hard carbon, very hard to graphitize. If you look at this first peak, it comes about from the Somebody needs to turn off their microphone. Oh my God. If you look at this first peak, which comes about from the parallel stacking of graphene layers, you know, its half width is big. There's only a couple of graphene layers stacked in a parallel fashion here. And the half width sharpens somewhat by 1400, but not a lot. Okay, so from this you can take away that there aren't many graphene sheets stacked in a parallel way. Now over here, this is small angle X-ray scattering for a graphite sample called Fluka, and then these sugar samples heated between 900 and 1400 degrees C. So most of you probably are not familiar with small angle X-ray scattering. So I'll interpret for you what this graph means. if you have a sample that has no internal porosity at all, just a bulk sample, and you do small angle X-ray scattering on it, you'll get this curve that's a straight line on a logarithm of the X-ray intensity versus Q. What is Q? Q is like scattering angle, and a Q of 0.1 is a scattering angle somewhere around 5 degrees or so. Okay, so it means that the intensity drops off like a power law. Now, if you have samples that have internal porosity, then you get a hump like this. And the position of the hump tells you about the characteristic size of the pores. And the further the hump is to the right, smaller the pores are. So you can see what happens, that as you heat from 900 to 1400, this hump shifts to the left. So it means the pores are getting bigger. Okay, so at 900, there's internal porosity in this heated sugar, and there are not many parallel stacked graphene sheets. And by 1400, the pores are bigger. Maybe there's a little bit more parallel stacking. So what's going on here in these materials? So Yuan Gao, a postdoc, and I proposed this model for what's going on. We call it the falling card model. So it's like spending the time to stack a house of cards with playing cards on your table. And then what would happen if, one card falls over? So the idea is, look, these hard carbons don't have parallel stacked graphene sheets. So if each one of these straight lines is a graphene sheet, if they're not stacked parallel, there has to be internal porosity. I mean, that's pretty simple. And we know that when we heat graphites, more layers become parallel stacked. And for hard carbon, it takes very large temperatures for this to happen. But, between 900 and 1400, some of these sheets can fall into parallel stacking, shown here. So you get more parallel stacking, and when this sheet falls over, the pore becomes bigger, right? So it's just a simple hand-waving model for, what happens when you heat a hard carbon. The internal porosity actually gets bigger. So that's kind of cool. The average pores become larger. So I've given you a homework problem on homework 2 about the falling card model, because it's characteristic really of my career, which is do things as simply as you possibly can and good things happen. Like this model is an absolute baby model, but people like it, and they cite the paper and use the concepts developed there. So here's another interesting observation about these sugar carbons heated from 900 to 1400 degrees C. Okay, so this figure on the left shows how much carbon dioxide can be absorbed into the sample as a function of the partial pressure of carbon dioxide. So from vacuum up to 1 atmosphere partial pressure of carbon dioxide. And this measurement's done at room temperature. So for material heated at 900 degrees C, look at this. This is pretty incredible. You can absorb 60 milliliters of standard temperature pressure carbon dioxide, 60 mils, into 1 gram of this carbon, 60 mils per gram. A gram of this carbon would take up about 2 mils of space, powdered heated sugar. So it's quite incredible, right? And that shows you how much internal porosity there is, and the CO2 absorbs on the surfaces of these graphene sheets that make up the pore walls. And then as you heat to 1000, not much change happens. You heat to 1100, you can see there starts to become a hysteresis loop between the adsorption and then the desorption of the CO2. And that's an indication that the openings to the pores are getting small, about the size of a CO2 molecule. So it's harder for the CO2 to get in, and then once it's in, it's tougher for it to get out. So there's a lag in desorption. As you reduce the pressure, the CO2 doesn't come out as easily. And when you heat to 1200, it gets even worse. You know, you can absorb less, and coming out through those very small pore openings is incredibly difficult. And by 13 and 1400, there's very little absorption of CO2 going on. And what's happened is the openings to the pores have closed. The pores are still there. You see them in small angle X-ray scattering, but the openings are becoming closed. Okay. So let's just go back 2 slides. 3 slides. So let's look at this, okay? At 900 and 1,000 degrees or 1,100, we have this very long low voltage plateau where lithium can go within this nanoporous carbon and come out at very low voltage. So it seemed to us at the time that if a lithium atom was just adsorbed on the surface of a graphene sheet, its binding energy would be very small. So that means its voltage would be very small, very close to that of lithium metal. There wouldn't be much advantage for a lithium to be on the surface of a single graphene sheet compared to being in lithium metal. You know, intercalated into graphite, the voltage is only about 80 millivolts. The voltage of this plateau is about 50. So it's about half one graphene sheet compared to 2. It's absorbed to the wall of these pores. And then if these pore openings start to close in the 1200 to 1400 degree C range, that plateau should disappear. And sure enough, it does. You know, so when we saw the correlation between the CO2 adsorption and the capacity of this lower plateau, we began to think that this lower plateau comes from adsorption of lithium on the surfaces of the pore walls in those micropores or nanopores. Any questions about that logic?
I just have a question. If at higher temperatures, your graphene sheets are getting more ordered, wouldn't that allow for more surface area that can be covered with CO2?
No. Let's look at the X-ray patterns here. So this second peak tells you a lot about the lateral extent of the graphene sheets. And it's sharpened up a little bit, but not really very much. So you don't have very many parallel stacked sheets from this peak. And everything's in turbostratic misalignment anyway. And you know that the lithium doesn't want to go into graphene sheets that are turbostratically misaligned. So, you know, you're not really making anything great at this temperature range. Okay, so now let's take a look at this graph on the right here. So what is this? This is the time it takes for the adsorption to become complete. So at 900 degrees C, I mean, there's nothing telling you here about how long this took, right? But if you just step the partial pressure from 0 to 1, and then you watch and see how long it takes for the CO2 to reach its maximum, it doesn't take very long. It takes about 600 seconds at 900 degrees C for the pores to fill. And then as you heat the samples more and more and the pore openings get smaller and smaller, it takes longer to reach the maximum amount. And this is normalized to the maximum amount, right? So, you know, you absorb less at 1200 and it takes a lot longer to fill up what you can. And by the time you get to 1400, it takes virtually no time to fill because you're filling nothing. You know, the amount of pores you fill is virtually zero, but that happens really fast. Okay, so this is telling you that the pore openings for CO2 and the size of lithium is different than the size of CO2, right? But for CO2, the pore openings are closing in this range between 1100 and 1400 degrees C.
Jeff,
Yeah.
I have a question about the difference here between CO2 and lithium. So this is adsorption from the gas phase, right? But in the other plot, like a couple slides back, where we saw the voltage plateau, does it also play a role whether electrolyte can enter those pores?
Yes, like this is really an important question. So if you look at this big irreversible capacity at the beginning, this can be because the pore openings are big and electrolyte can get in, and then you're getting a lot of electrolyte decomposition on the interior pore walls, which you don't want. And as you close off those pores, you know, the amount of irreversible capacity gets less and less. So selecting the pyrolysis temperature to give you a long low voltage plateau and minimum irreversible capacity is really important. And I think it's all about pore closure. It's pretty neat.
Thanks.
Yeah, so these are really interesting samples in that you can get large specific capacity out of them. But if you think about the the fact that there's all this pore volume in them, the volumetric capacity turns out to be crappy. Well, not totally crappy, but worse than graphite. So they never really became very heavily used. Okay, so I want to show you guys this experiment because this is really something cool. So this is a really powerful experiment that David Stevens did during his PhD. And this is in situ small angle X-ray scattering. This measurement was done on our D5000 in the lab. You don't need a fancy X-ray machine to do this. You could do it with our Bruker D8 just as well if you wanted. So what did he do? He had a cell and he measured the small angle X-ray diffraction patterns as the cell was discharged and charged. And this is with sodium intercalation, sodium insertion, not lithium. And sodium was used here because you know, sodium has more scattering power than lithium, and you can observe it. You can observe its impact as it goes into carbon. So let's take a look. So A represents the small angle X-ray scattering pattern taken at the beginning of the experiment when there's no sodium in the material at all, just empty pores. And you see this hump due to the pores in the nanoporous carbon. And then you go to B, which is adding lithium on this sloping part, okay? The sloping part. So we don't think the pores are filling on the sloping part because that's where, you know, the binding energy is larger, and that's where the sodium would be going in between the layers, the few pairs of adjacent parallel layers that you would have, and having, you know, reasonable binding. So by B, the original curve in A has been reproduced so that you can see that between A and B, there's no change, all right? But then when you go from B to C across this lower plateau, and then you look what happens, there's a big change. A big change happened. And in fact, it looks now more like a uniform material without porosity at all. And why is that the case? Well, because if you put sodium into the pores, then you change the contrast between carbon and an empty pore. There's a big electron density contrast there. The empty pore has no electrons, and the carbon that makes up the pore walls has a lot of electrons. X-ray scatter from electrons. So there's big contrast between the pore and the carbon, and that's why the hump is intense. But when you start filling the micropore with sodium, now the pore has electron density in it, and the intensity of the small angle scattering signal becomes less. So the difference between B and C tells you that the pores have quite, they fill quite a lot with sodium. It's cool. And then when you go back to D, the hump reappears. So you compare the original spectrum in dash to the spectrum at D, and you see the hump back again. And when you go all the way back to E, it looks very much like the original case. So this really was an amazing experiment that Dave did. And it really, for us, proved that the lower plateau is filling the pores as much as they can fill with either lithium or sodium. So any questions about this?
Question not specifically about this article, but is there a way to reduce that porosity if the hard carbon is graphitized under pressure?
Oh, I don't know the answer to that, Eric.
Okay.
If you did reduce the porosity, I think you'd reduce the capacity in this lower voltage plateau as well, which is not what you want to do.
Right.
Yeah. Yeah, you're sort of trapped in a box with these carbons because this nanoporosity is good for storing the alkali metals, but it increases the volume of the material a lot. So volumetrically, they're not that great. Okay, so now it says on the board, give a complete summary of what happens when hard and soft carbons are heated. Okay, give a vertical temperature axis and describe the steps. So I'm going to do this because I think it's kind of useful to do it as a review of what's going on here. And I'll go to my document camera to do this. My God, what's going on? Okay, I think you should see my document camera.
Yep, we see your document camera.
Okay, good. So I'm going to start at the top of the page and work down. And this will be soft. And this will be hard. Okay, so you start with a precursor in both cases. And as you heat up to about 500 degrees C, the main things that happen are hydrogen loss in both cases. And in the case of soft carbons, you have a fluid phase. Over here, you don't have a fluid phase. All right. So then what happens here is you get some alignment of aromatic sheets. And at this point, they're small. So maybe LA, that's called the size of the graphene sheet in the plane of the graphene sheet, is a small. Maybe it's 2 nanometers or 3 nanometers. And over here, you don't have any alignment of the sheets at all. So it's aromatic sheets are, if you like, randomly stacked. And then when you heat more, maybe to 1200 degrees C. Now you have lots of parallel sheets. They're all in turbostratic misalignment. So that means P equals 1. P is the probability for turbostratic misalignment. And by 1200 degrees C, the hydrogen to carbon ratio might be very small, like less than 0.05. For the hard carbons, when you heat to 1200 degrees C, you have almost no parallel sheets. So you have a sort of house of cards type of carbon. House of cards. And if you do have some parallel sheets, a couple of them, still its P is equal to 1. They're randomly rotated relative to each other. And the hydrogen carbon ratio is basically the same. Now we heat to 2000 degrees C. For the soft carbon, what you have is large graphene sheets, parallel stacked, but P is still equal to 1. And the hydrogen to carbon ratio will be very small. I don't know what it is, small. Less than small. At 2000 degrees C for the hard carbons, you still have, now you've got, when you heat in this range, you have a pore closure. So they become really crappy for battery electrode materials in region 3. And, you know, some little bit of parallel stacking. And P equals 1. And then finally, as you go from 2000 to 3000, for the soft carbons, what happens now is P goes toward 0 as T increases. So during this temperature range, you're really just rotating the sheets into AB stacking.
Jeff, can you move it
Yeah.
up a little bit? I can't see.
Like that? How's that?
A little more. Okay, yeah, it's better. Thanks.
That's as far as I'm going to go. The problem is when I'm doing this, I only see a thumbnail of what I'm doing. So, and it's backwards too. It's reversed, left to right. It's mirrored. So it's really bad. I have really no idea what you guys are seeing. So your comments about what you can and can't see are very useful. And over on this side, when you go to 3000 degrees C, you know, eventually you get, you know, reasonable amount of parallel stacking. But P is still almost 1. So you just don't eliminate turbostratic misalignment in the hard carbons. They just don't graphitize, is what the jargon would be. And it all comes about way back in the beginning where there was no fluid phase that forms, and you sort of lock the carbon into sp3 bonding at certain places. And then it's just really hard to have it, you know, have all these sheets align and graphitize. So that's kind of a story about how these carbons evolve with temperature. I'll send you this piece of paper if you were unable to copy it down. But you'll find that in something like this in most books on graphitizing carbon, but they won't typically talk about P because you need to measure this probability for turbostratic alignment with relatively sophisticated X-ray software, which, by the way, we have in the lab, and I think there's no one remaining in the lab but me that's trained on this software, but it's really easy to use, and I can train anybody if anyone's interested in measuring probability of turbostratic misalignment in their carbons. Okay, any questions on this before I go back to the PowerPoint?
Yeah, I have a question, Jeff.
Yeah.
So we know hard carbons don't have a fluid phase. Is it possible to maybe mechanically make the hard carbons really, really small to the point where it could almost act like a fluid phase? Or is that not possible?
Don't know. I don't know the answer. So you're basically saying grind the heck out of the precursor, make it nanometer size, and then heat it up and see what happens.
Yeah.
I don't know what would happen. I don't know. I would be surprised if it hasn't been tried by someone somewhere, though.
Okay, thanks.
All right, I'll share my screen again. Oh my God, it's gone. I just don't understand this. I don't understand why these other PowerPoints show up. It doesn't make any sense. Let's see what happens if I do this. There we go. Okay. So now I want to talk about lithium titanate for a few minutes, okay? So lithium titanate is another negative electrode material that's used. It has the same structure as LiMn2O4, which we talked about in the positive electrode material structures part. So if you look at the stoichiometry, 4/3, 5/3 compared to 1 to 2, it means that 1/3 of these lithiums are sitting on the sites where the titanium atoms are. So 1/3 plus 5/3 equals 6/3, which equals 2. Okay, so this just means there's some lithium on the titanium sites, or where the manganese is in LiMn2O4. So that means you should write the material like this, where the brackets enclose the atoms that are on one type of sites. And it has mobile lithium in the 8A sites in the crystallographic nomenclature, just like LiMn2O4. And when you can add a further lithium to this, and it goes to being lithium-2. And the structure of lithium-2, Li 1/3 Ti 5/3 O4, is just like spinel lithium cobalt oxide or spinel lithium TiS2. Okay, so we haven't learned yet about spinel lithium TiS2, but you can make lithium TiS2 in a spinel structure, it turns out. And I'll talk about that in a few more lectures. And it has mobile lithium, and this thing's called LTO by the battery people. So this is a figure from one of Tom Ozuku's really nice papers. I don't know if I've talked about, oh yeah, I have talked about Tom once before, but he's a guy that I would say is a lot like me. He likes simple stuff, simple experiments, very, very trustworthy data. Anything Tom Ozuku publishes or published, he doesn't do much anymore, you can trust it. It's absolutely rigorously good. Anyway, this is a figure from him that compares voltage curves of different positive electrode materials and also lithium titanate. So E is lithium titanate. So it's around 1.5 volts versus lithium metal. So you can use it as a negative electrode material instead of graphite. But you pay a penalty. You pay a 1.5 volt penalty. So you could make an LFP LTO cell. This is lithium iron phosphate here, D, and you get about 2 volts only. But it would have a very flat voltage curve. Yeah, so the point is LTO sits right around this dashed line here. So when you use LTO as the negative, you give up almost 1.5 volts relative to graphite. Now, there are advantages of using LTO, and that there's a couple. The first is you're far away from lithium metal, and it means that LTO is far less reactive with the electrolyte than lithium intercalated in graphite. So if you want to make a long lifetime cell, using LTO is a good choice, but you pay a big penalty in energy density. The second thing about LTO that's good is you're very far from lithium metal. So when you recharge cells with graphite really fast, due to over voltages, you can push the potential below the lithium metal potential and plate metallic lithium onto the surface of the graphite. That's very bad. But LTO is 1.5 volts away from lithium metal. So it's virtually impossible at any charging current to plate lithium on an LTO negative electrode. So if you want to make cells that can be charged fast, have a really long lifetime, and you don't really care enormously about energy density, LTO is your choice. I'll tell you a little story. I've interacted with a company called Medtronic for a long time. They make implantable biomedical devices. One of the things they make is a neurostimulator. A neurostimulator, when it's implanted into the body, you want it to stay in there as long as possible. And the Medtronic guys make a technology that has lithium titanate as the negative and lithium cobalt oxide as the positive. And it's only charged to 4.05 volts. Okay, so they keep the charging voltage very low. I've seen data from these cells from Medtronic. 10 years of cycling at 37 degrees C, body temperature. 10 years of cycling. Cells have lost 1% capacity. 1% in 10 years of operation at body temperature. So you can make a really long-lived cell with lithium titanate. Yeah, so just coming back to this for a minute, you know, when you have a positive electrode and a negative electrode in a lithium-ion cell, the full cell voltage is the difference between the red curve and the blue curve. The scales are different here. The blue and the black correspond to the right-hand axis, and the red curve corresponds to the left-hand axis. And when you're discharging the lithium-ion cell, the lithium ions empty the graphite and fill the positive. They want to be in the positive. They're more tightly bonded in the positive. So that's what happens spontaneously when you connect the wires. The lithium moves through the electrolyte as ions, electrons in the wire, and the positive gets full. Okay. So the reason I'm showing you this graph is because if you want to have a full cell with a decent voltage, the negative electrode voltage should be near zero, right? And this is one of the reasons the region 1 carbons were never used for anything, because you know their voltage is up at 1 volt negative during the discharge. When you're discharging the cell, that's removing the lithium from the graphite, from the negative side, and that happened at 1 volt. So you would give up a volt. So why am I showing you this? It's because you can get really annoyed at scientific journals. So here's a paper. This is in a Journal of Alloys and Compounds. It says high capacity nanocarbon anodes for lithium ion batteries. So you look at this thing. We'll take a look at panel B. You insert lithium, starts at 2 volts as a sort of a curve, goes down to 700 milliamp hours per gram. Not too bad. But look what happens when you remove the lithium. It comes out at an average voltage somewhere around 1.8 volts. This whatever this MPG is in the same paper, now you have 1,000 milliamp hours per gram. But look where it comes out, an average voltage around 1.7 volts. Look at the huge difference between the first reaction of lithium and the second. There's all this irreversible capacity, which is lithium that's been chewed up in reactions with the electrolyte. So this stuff presumably has a huge surface area that's accessible, and it's terrible. Okay. So these type of carbons are useless. Do you think this is useful? The answer is no, it's not useful. Here's another paper. Okay, this is from a famous journal, Nano Letters, high impact journal. Right? Would you like to publish your papers in journals that publish stuff like this? So here's the lithium going in, 700 or 800 milliamp hours per gram compared to graphite, but look where it comes out. The average voltage is like 2 volts. It's completely useless. This is a quote from the paper. Therefore, these nanosheet forms of graphene are promising anode materials for future large-scale, high-capacity lithium-ion batteries. More than 1,400 citations. Totally useless. Who were the reviewers? Okay. These are things you have to ask yourself when you see stuff like this. You just think, what the hell? You know, and as we go on in the course, I'll give you a lot of papers on homework assignments, whatever, 4, 5, 6, 7, and 8, where you have a chance to be pretty critical about certain papers. Okay, so that's all I've got on the negative electrode material stuff. So if anybody has any questions, it's a good time, because I'm going to move on to the next part.
Actually, Jeff, yeah, real quick, I didn't quite understand why how you can tell that the material is not good on these charts.
Okay, so look at this. When you are removing the lithium from the material, that's these curves where my mouse is going over them.
Yeah.
Okay, and that corresponds to the discharge of a lithium-ion cell. So that means you're paying on average a 2-volt penalty, 2 volts versus lithium metal. So your positive's at 4, and now your average voltage, so the positive is 4, say the positive is 4 is a flat line. The voltage curve of the lithium-ion cell would start at 4 and end somewhere around 0.7, a huge swing in voltage. Nobody wants that. And also, the energy densities become terrible because the average voltage is only 2 volts. Is that helpful?
Yeah, thank you.
Yeah, and think about the energy hysteresis, right? You'd be charging the cell between 4 volts for the positive, and then this is the curve the negative follows during charge. It'd be 4 volts during charge and 2 volts during discharge. The thing is 50% energy efficient. Total garbage.
Got it.
Okay, cool. Any other questions?
I have a quick question about the Medtronic thing. What were the electrodes in there? That cell that was only losing 1%.
The electrodes are LTO and LCO.
And it goes to 4 volts, did you say? Or you mean LCO voltages?
4.05 volts versus lithium metal on the LCO side.
Oh, okay, got it.
Yeah, pretty good, right?
Yep.
I can show you the data. I've got it somewhere on my computer. It's incredible. You just think to yourself, holy God, this is incredible. But that's what you want implanted in your body. You don't ever want to have to take it out.
Yep, awesome.
Okay, any other questions? If you guys keep asking questions, we won't have to go on to the next part. Okay, we'll go on to the next part just for a few minutes. Okay, I have to open up another PowerPoint. Here we go. Okay, I don't know if you can see this new PowerPoint or whether I have to close and open again.
We see the old one.
Okay, I'll close. And then I'll share again. Okay, now you should see the new one. Is it possible?
Yes.
Yep.
Okay. So I'll start by telling a story. So all this work was going on in the late 70s about titanium disulfide and vanadium sulfide, and good enough lithium cobalt oxide came out in 81, you know, and everybody noticed the voltage of the electrode, the intercalation electrode, varied with the amount of lithium that you put in it. They all have sloping voltage composition curves, right? So when I went to UBC as a graduate student in 1978, nobody really had a good picture of what was going on. Why did the voltage vary with lithium content in these electrode materials? In addition, when you think about it, when lithium goes into graphite or into NMC or NCA, you know, you're changing the composition of the material, you're changing the electronic properties. As an example, people in our lab that have taken lithium ion cells apart at the top of charge, when the lithium's in the graphite, they know the graphite's gold. It's gold in color, whereas graphite without lithium is gray. Everyone knows that. And you've changed the graphite from a semi-metal, when it has no lithium in it, to a metal when it's full of lithium. And nobody really understood how to think about the electronic structure changes in these materials. So this guy here, Ross McKinnon, he was already at UBC when I got there. He's a Dalhousie bachelor's graduated I think in 1976 from Dal, and then did a master's at Dal and then went to UBC for his PhD. It's the same path I followed, and we went to the same lab for our PhD. This guy is incredibly smart, and I was really fortunate to be in the same lab with him at the same time. And when he left to go to the National Research Council in 1980, I followed him there in 82 because we worked really well together. I always said to people, I was the hands and he was the brains. And what Ross did in his PhD thesis was really try to explain the fundamentals of what's happening in intercalation materials when you add lithium or you add sodium to a host. What changes? Like, why does the voltage change? How do the electronic properties change? All this stuff. And, you know, he was a very shy guy, didn't go to many conferences, but his PhD thesis for me is really one of the best documents around about the physics and chemistry of intercalation materials. And I've sent you chapter 4 of his thesis, and I've also sent you, I will send you chapter 7 later on when we get to that part. And I have several copies of the thesis in the lab, and you know, it's really worth reading it carefully and thinking carefully about it. And it's not like reading a novel. You have to sit down and spend the time. But the most amazing thing about this thesis is that this thesis predates almost all the experiments that it predicted nicely. Okay, it's incredible. At the time of the thesis, nice model systems had not yet been found. So Ross calculated all these things and he said, you know, if this happens, this should happen. Well, no one had observed this happening yet, whatever it was. And I'll explain a whole bunch of these things. But then as time went on and we started looking at more and more systems, we started finding all the things he predicted. So it's a really wonderful document. So Ross worked at the National Research Council in this battery electrode space probably till about 1988. And then he did a sabbatical at Bellcore. So Bellcore was an offshoot of AT&T Bell Labs. And he worked with Jean-Marie Tarascon. Okay, so Jean-Marie Tarascon, who is a very famous guy in our field, Ross went to do a sabbatical with him on these battery materials, okay? And right at that time is when high temperature superconductivity was discovered by Stephen Chu and others. And Jean-Marie Tarascon just jumped in there because he's a solid state chemist by training. He started making these materials left and right. For those of you that make samples, Jean-Marie would put 10 samples in tiny crucibles, line them up in a boat, 10 of these lines, that's 100 samples in a box furnace per day. Okay, 100 per day. 100 per day, crazy. Anyway, Ross got involved in high temperature superconductivity, and then he never came back to the battery field at all after that. It was a loss, really, for all of us. So that's kind of a story, because I didn't really want to start on the meat of this stuff and then just leave it. So if you have a chance to read his thesis or look at any papers that he's written, they're all works of art. They really are. All right, so that's all I'm going to do today, and I'll see you on Friday virtually.